Alright, today we are talking about continuity.
More like continuity.
Oops. Continuity comes from the word continuous. Well, okay. So, a continuous function has no holes, jumps, or vertical asymptotes. Okay? A continuous function has no holes, jumps, or vertical asymptotes. What that means is you can draw it without lifting your pencil. Okay? So there's no break in the function. You can draw the whole function without lifting your pencil. Okay? So there's no holes to jump over, there's no asymptotes to jump over, there's no jumps to jump on. Okay? So let me just put up a little graph here. Let's say we have something that looks like so let's call that 1, 2, 3, 4. Let's call that 1, 2. Okay. So where is this function not continuous? At x equals 1, x equals 2. Okay, that's it, right? So at x equals 1, there's a jump discontinuity. I'll talk about the type in a sec. At x equals 2, there's a hole. Okay, even though there's a point somewhere else, it's discontinuous here. So notice how where there's a jump at x equals 1, the limit doesn't exist and it's not continuous. Alright? But at the hole at 2, the limit does exist and it's still not continuous. Okay, so that's a difference. We'll make a little table for that here in a second. Alright? So for continuity, the official definition for continuity is that the limit as x approaches c of f of x equals f of c. Okay, can somebody maybe explain what that actually means? Nope.
The limit.
Let's call this c. Okay, we're going to call that c.
The limit of y as x approaches the x value c is the same as if you were to plug the x value c into the function.
Right. So if you have a function, let's say you have this function, okay, the limit exists, the limit as x approaches c, there might be a hole there, you can still have a hole with a limit, but what this says is that at that point, that limit, that y value, is also the function value, which means that that's where the closed dot is also. Okay, so basically that's saying we're filling in that hole and then now it's continuous. Okay, so as long as the limit, which is the y value as you approach from both sides, so we got the y value as you approach from both sides, as long as that limit is equal to the actual function value at that point, then the function is continuous. All right. If those two things weren't equal to each other, then you would have a hole there. All right. So let's talk about the discontinuity types, the types of discontinuities. So
Well, where does that come from?
That comes from that comes from discontinuity. Okay. So where you have discontinuities pretty much always involve, well, almost always involve a denominator of a fraction, because that's where things can't happen. That's where you can't have x values, okay? So we're going to look at where a denominator equals 0. Now there's different situations here. If the denominator equals 0, but you can factor and cancel that, which you've done a bunch of that already. If the denominator is 0, but you can factor and cancel it, that makes a whole. Okay? So this is going to be a whole. Okay? Now, so I'm calling it a whole. That's what I call it. But the technical term for that is a removable that comes from remove.
Didn't know we were getting it.
Alright, so that a whole is also called a removable discontinuity. Okay? Now the reason why you can remove the discontinuity is because you can, when you factor and cancel, that's kind of what you're doing, is removing that discontinuity. Okay, but that whole is still there. So you can remove a discontinuity. It seems a little weird, but you can remove the discontinuity by filling in the hole, and then that makes it continuous. Okay? So a hole is a removable discontinuity. Now, if the denominator equals 0, and you can't factor and cancel, or let's just say you can't cancel, because you might be able to factor, but let's say if you can't cancel it, okay? We've seen these before. What do you have when you get 0 in the denominator of anything that you can't cancel?
A black hole.
What do you have on a graph at that point? You have a vertical asymptote. Okay? A vertical asymptote. Alright? So both of those have a denominator equal to 0, so that would be something like this. Okay. So if you can cancel it, it's a whole. If you can't cancel it, it's a vertical asymptote. All right. And now the type of discontinuity for a vertical asymptote, that is actually called an infinite. That comes from fin. Doesn't it? No? Isn't that French for end or something? So there's no end?
If we're going to go to a different language, you might as well go all the way back to Latin.
Okay.
It comes from physique.
Oh, it does? Okay. All right, so a hole is removable discontinuity. A vertical asymptote is an infinite discontinuity. Okay. And what was the other thing? What was the other thing that you can't have for continuous?
Jump.
A jump. Okay. So a jump. You guys know what a jump is. That's just, you got to tell that from the graph or from the piecewise, and that's called a jump discontinuity. Okay, so that one's pretty straightforward. There's nothing really about the equation here except that it would have to be a piecewise function. Okay, it would have to be a piecewise function in order to have a jump discontinuity. All right. Okay, so let's say, let me look at this assignment sheet here. let's say we have the function f of x equals x squared minus 9 over x minus 3. Okay. Does this have a discontinuity? Yes. What kind is it? It's removable because this can be factored and canceled. Okay. So, yes. Because it has a denominator that can be 0. So anytime the denominator can be 0, you have a discontinuity. Okay. It's going to be one of 3 types. It's either got to be, well, in denominator involved, it's either has to be a vertical asymptote or a whole. And it's a whole because you can cancel it. Can't cancel it, it'd be a vertical asymptote. Okay. Now, one particular type of question that you'll be dealing with is, what's the y value that you would need to put in there so that there wasn't a hole anymore? Okay, so in order to remove that discontinuity, what would the y value have to be? All right. So this right here, x cannot equal 3, right? X cannot equal 3. So what we need to do is create a piecewise function to do that. All right. So to create a piecewise function, just add a bracket, and we need to define this separately at x equals 3 in order to have a point that fills in the removable discontinuity that's there. Okay, so we got to figure out what that point would be, but that's easy. All you got to do is do what you did before: factor, cancel, plug in, and that gives you the y value that you would have had if there wasn't a hole there. So that's the y value here. So if we factor and cancel, we're going to have x minus 3, x plus 3 over x minus 3. Those cancel. We plug in 3. We get 6. That's the value, the y value. That 0.36. That's where the hole was. Now when you break it up into a piecewise and define it separately, that's still a function. Now it's a continuous function because we've filled in that hole. Okay. It makes that function continuous. So what would that look like? Well, that original function is going to look like there's a hole at 3 and it's going to be at 6. So there's a hole there, it has a slope of 1. So that's right there is what the top part of this piecewise looks like. It looks like a line with a hole at x equals 3. Well, what does this do? This 6, this function of 6 at x equals 3 just fills that in, and now it's continuous. Okay? Sound good? Okay. So I have a handout for you, and I'll tell you which ones to do.